Hello and welcome back to Complex Analysis. And first I want to thank all the very nice people that support this channel on Steady, via PayPal or by other means. Now, in today's part 7, I show you examples for the famous Cauchy-Riemann equations. For this, let's first recall the important theorem from the last video. There we introduced the Cauchy-Riemann equations with respect to the complex differentiability. Hence, we can immediately reformulate the theorem for holomorphic functions. And as always for this, we have to choose an open subset U in C. And now you should already know, a complex function can be equivalently described as a function from R2 into R2. However, in this case for the new function, the domain should also be an open subset of R2. So maybe let's simply call it UR. Obviously, when you visualize U and UR in the plane, they look exactly the same. In other words, the open domain here does not make any problems at all. Okay, now in the last video we have learned that we can split up the function f into a real and an imaginary part. And both we can see as a function from UR as a subset of R2 into R. In particular, the real part function here we denote by a lowercase u. So please recall, this u is a real valued function. And then, exactly in the same way, the imaginary part of f gives us a function we call v. So also here, we have a function with domain ur and codomain r. Hence you see, the whole information of the function f is now translated into these two functions. Indeed, the property that f is holomorphic translates into the fact that u and v fulfill the Cauchy-Riemann equations. These are not complicated at all, they are just two partial differential equations. The first one simply says that the partial derivative of u with respect to x is the same as the partial derivative of v with respect to y. And then in the second equation you see, when you switch the roles, there is a minus sign included. In summary, what we need for a holomorphic function is that these two equations are fulfilled at each point in the set UR. In fact, this equivalence here we have discussed in the last video. Now in this video I want to show you concrete examples. And I would say, let's immediately start with a very simple one. So let's take the complex function f from C to C, given as the identity. Which means the number z is simply mapped to z again. Now, because we want to deal with the partial derivatives with respect to x and y, we have to write z as x plus iy. Hence we do this change on the left hand side and on the right hand side. And then you see, here the real part is our function u and the imaginary part is our function v. So you see, in this case, it's not complicated at all. And now we just want to check if the Cauchy-Riemann equations are satisfied. So let's write down the partial derivatives. First we have du dx, which is in this case simply 1. In the same way, we also see that dv dy is very easy to calculate because this is a simple function and the derivative is just 1 again. Hence we immediately see that the first equation is satisfied at all points. So let's go to the second equation where we have du dy. There we see there is no y in u, therefore we get 0. In fact, the same holds for dv dx because there is no x in v. And also of course the minus sign does not change anything. In summary, both Cauchy-Riemann equations are fulfilled. From that we then can conclude that the function f is holomorphic. Of course, this is a fact we've already known. Therefore, I would say in the next example, let's look at a function where we already know that it is not holomorphic. Indeed, this was simply the complex conjugation. So f of z is z bar. Now, as before, in order to apply the Cauchy-Riemann equations, we have to rewrite that with x and y. Of course, this is not so complicated. The imaginary part just gets a minus sign. And then as before, the real part is u and the imaginary part here is v. So you see, it's different from before, and it will change the first Cauchy-Riemann equation. Of course, here the u dx is still 1, but dv dy is now minus 1. Therefore, we can conclude this is not the same. Indeed, no matter which point we put in. In conclusion, we get the result we've expected, namely f is not holomorphic. Here you see, showing this was very simple by just using the Cauchy-Riemann equations. However, maybe we should also look at a more complicated example. So let's take another complex function f. And now I want to look at it as z squared plus iz. To be honest, you already know that this is a holomorphic function, because it's a complex polynomial. Indeed, we already know how to calculate the complex derivative for such a complex polynomial. Here it should be 2 times z plus I. Still, it's very helpful to check it with the Cauchy-Riemann equations. Now, by writing x plus iy instead of z, we actually have something to do now. Because in this expression here, we don't see immediately the real and the imaginary part. We first have to calculate a little bit. However, that's not so complicated, we simply can do the whole calculation here. So we have x squared plus I times 2 times xy minus y squared from the binomial plus I times x and minus y. Now let's put the real part to the left and the imaginary part to the right. So the real part is everything without an I, and for the imaginary part I factor out one I. And then we have the result we wanted. Because again, here we have our function u and there we have the function v. Now with these two functions we can check the Cauchy-Riemann equations again. First, the u dx, not hard to see, it's simply 2 times x. Then the second partial derivative we want to calculate is dv dy, which is also 2 times x. Hence, our first equation is actually fulfilled. Going to the second one, you see we have to do a little bit more because this derivative is minus 2 times y minus 1. Okay, then the last derivative we want to calculate would be the partial derivative of v with respect to x. And there you see, it's 2 times y plus 1. And then for our equation, we just have to put a minus in front. And then we recognize this is the same as du dy. Therefore, also here, both equations are fulfilled, so the function f is holomorphic. I already told you, this is not a surprise for us. However, with this example, you have learned how you can apply the Cauchy-Riemann equations when the function f is given as a real and an imaginary part. And in fact, you also get the complex derivative of f from these partial derivatives here. But I think this is a good topic for the next video. Therefore, I really hope that I see you there. Have a nice day and bye.